So yeah, thank you. Thank you, Shazia. All right. So we'll start the recording. And what we will do is now I will start off with the finitely deep, not finitely deep, infinitely deep squares. Okay. I'm not in my best shape today. So please, yeah, just bear with me. All right. Okay. So now, if you, what do you really need to remember? Okay, so I do have some notes, but again, the scanned copies have come out horrible. So I'm going to take advantage of that I have this iScribe and just scroll out a few things so that you will know what is important to remember. Okay, so let's just go and share screen again. Okay, there's the iScribe. Share. Yeah, it's visible for everybody. Yeah, so I will just change the page and we will go to the infinitely deep square well. Okay, we will essentially look at various problems with link to this. Now, first of all, what does the potential of an infinitely deep square well look like? Okay, so pictorially, if you think about it, you obviously know that this is your x-axis. You're going to be plotting your potential on the y-axis, along the y-axis, sorry. So you essentially have two positions, okay, at x is equal to 0, let us say, and maybe I will put this as x is equal to L, okay, x is equal to L. So this is your v of x that you're plotting. And in both these cases, it goes off to infinity. It is also infinity for x greater than L. It is also infinity for x less than 0. Okay. And in between x is equal to 0 and L, it is essentially a constant. Or we can take that constant to be 0. So essentially, how do you write this? V of x is equal to 0 for 0 less than equal to x less than equal to L, and it tends to infinity for x less than 0 and x greater than L. Okay. Now, what does it essentially tell you? Of course, it tells you that your psi x in the regions where the potential tends to infinity is going to go to 0. Okay. So it will be equal to 0 when x is less than 0 or x is greater than L, or in other words, your psi x is square, mod psi x square, is also going to be 0 in these regions, right? So you will never ever find the particle, okay, in regions which are x less than 0 or x greater than L. So effectively, your particle is confined between the limits of x is equal to 0 and x is equal to L. So that is like you've put it in a one-dimensional box, correct? Yeah. And if it is in the one-dimensional box, it is going to just sit inside the box. Now, inside the box, Vx is equal to 0. So it is essentially like a free particle, okay, within a 1D box, okay, um, from, so this is essentially the extent of the box, x is equal to 0 to x is equal to L. Okay, so this is essentially what we have. We have a free particle. Now, so it is a free particle inside the box, but what do we really need? We essentially need to pay, attention to the boundary conditions, right? So what are our boundaries? One is, of course, x is equal to 0. The other is x is equal to L. And what we know is that our psi of x should be continuous. Continuous. And also we know that your d psi x dx should also be continuous. Should be continuous. Right? This is what we know. Okay, so these two things should be continuous. Now you basically, do this, all right? Now, if you remember, you essentially try and solve it like this. You put in the initial solution as equal to some a sine of x plus b cos x, correct? And you can ask immediately, why aren't we using a e to the power of ikx? Okay, the usual free particle thing that we did. Okay, why not this? Okay, is the question. And the answer is that this is actually very difficult to simultaneously set to 0 at the boundary conditions. Okay, yeah. Please remember, you will need your x of 0 to be equal, psi of 0 to be equal to 0. You will also need the psi of L to be equal to 0. And that is actually a very difficult thing to do with this particular form of the wave function. So you go for this. All right. And when you go for this, finally you end up with a solution. So I'm going to write down the final solution. So essentially, it's a matter of convenience, okay, that you go for this. And in quantum mechanics, finally, you choose those solutions which are convenient for you also, right? I mean, physically correct and they're convenient to work with, all right? And these guys also remember there is another problem with it. The other problem is that, see, first of all, your A and B will both, you will not be able to set to 0, correct? Yeah. And then you will run into issues of them, one of them running off to infinity or minus infinity when you go to very large distances. Okay, so that can be also an issue, because these are after all plane waves, right? Yeah. So you need solutions which are essentially going to decay off in the distance, all right, at least. So now over here, what solution do you take? You basically get sine of x is equal to, and this is your normalization constant, root 2 by L, and then you have sine of, this is n pi x by L. Okay, so this is the solution that you should remember, all right? And what is the energy? The energy, of course, it gets quantized, right? And what is the quantized energy? You will get essentially h cross square pi square by 2m. And then you have over here an n square by L square. Now, I would say that this is the part that you really need to remember, the n square by L square. Okay, especially if you're solving problems and you're doing them rapidly. Okay, even if you forget this part, okay, at least if you remember the n square by L square, it is going to help you. Why do I say so? Because remember, the mass of the particle is not going to change, and the other three are really constants, right? H cross is a constant, pi is a constant, 2 is a constant, right? So m will not change. So these are essentially constants. It's some constant multiplying n square by L square, all right? So what you need to remember is that the energy of the n state goes as n square. This is the most important thing to remember. And of course, the length of the well is again something that may be varied. You may be asked to compare more than one well, all right? And in that case, you need to remember it also goes as 1 upon L square. Okay, so these are the two things that you really cannot forget. So you need to remember this. You should remember this. And even for a moment, if you forget the exact formula, you need to remember these two. Okay, absolutely essential, especially the proportional to n square. So now what we have to remember is that there is really your n. Okay, what is your n? It is essentially, of course, a positive integer. Okay, and it starts from 1. Okay, it starts from 1, 2, 3, and so on and so forth. Right? Now, obviously, there is no E0, there is an E1. Okay, and what is that E1? That E1 is nothing but h cross square pi square by 2m L square. Okay, then your E2. Okay, so this is, of course, your ground state energy. Now, what you have to remember is that your E2 is going to be 2 square E1, or it is equal to 4E1. Okay, and then your E3 is essentially 9E1. Okay, your E4 is 16E1. Now, very, very important. a lot of people draw the energy levels of a infinitely deep square well and they space them evenly. Okay, it's absolutely wrong. Please don't do this, especially in an interview situation. All right, people are not going to like it. Okay, so remember that if this is your infinitely deep well, I'm just doing a representation. Okay, if this is your E1, okay, then please mark out things in terms of the E1. Okay, and this will be your E2, which is going to be equal to 4E1, right? So this is 1, 2, 3, 4. Then you have a 5, a 6, a 7, 8, and 9. And here comes your E3, which is going to be 9 times E1. Okay. So please look, they are not at all evenly spaced. Okay. Kindly do not evenly space them, especially if you're plotting them. You should not be doing it even to yourself. If you don't do it to yourself, then you will not even do it in an interview situation. Okay, so the levels of infinitely deep square well, the levels keep going more and more apart as you go higher and higher in energy. Okay, point number one. Second is that, is there an upper limit to the energy eigenvalues? And the answer is no, not for an infinitely deep square well. So let me just say that when you come, so since I haven't really, I will earmark a few problems on the finitely deep square well as well. All right, so let me just go here. All right, so the key difference, all right, so I will say the key difference between infinitely deep square well and finitely deep square well is this. Okay, so what are the key differences? The first thing you have to remember, so let's me again plot the thing for the infinitely deep square well. All right, so you have, as I said, your E1, this is your first energy level, and then you have 2, 3, 4. This is your E2, which is also equal to 4 times E1, and then 5, 6, 7, 8, 9. And this is 9 times E1, which is equal to your E2. And then, of course, it continues. All right. So the basic thing is the number of bound states. Okay, the number of bound states for an infinitely deep square well is infinite, right? So you have actually essentially infinite number of energy eigenvalues, right? Infinite number of energy eigenvalues, right? So what about in a finite well? In a finite well, it is essentially fine. It is finite. What are the parameters it depends upon? It depends upon, in the finite well, it depends upon the length of the well, and it also depends upon the height of the potential. Okay, and if you remember your solutions from first semester, I don't remember exactly how it goes. I know it goes as V naught, and it's inversely proportional to the length. You essentially come up with something called as a strength parameter. Okay, and it's that strength parameter which will tell you, the stronger the strength parameter, more the number of bound states. The weaker the strength parameter, less the number of bound states. Okay. So this is one key difference between an infinitely deep well and a finitely deep well. Okay. So it is a good thing to keep this in mind. Infinitely deep well has an infinite number of bound states. A finitely deep well, on the other hand, has only a finite number of bound states. And that finite number depends upon the length or the width of the well. I won't say length of the well. Let's put it as width of the well. Sounds better. Width of the well as well as the height of the potential, right? Also, another thing which you have to remember is that you check for the infinitely deep well. Your ground state wave function is essentially just a sine function which is going to 0 at x is equal to 0 and at x is equal to L, right? Let's take now the case of the E2. You have actually a node at the center and essentially it goes something like this. Okay, I did it all wrong. I have not normalized it properly. It should actually be flatter than what it is for the ground state. What about the situation here? There will be two nodes, all right? And you will have a situation like this. Okay, I'm sorry, I didn't make it cross too well. All right. Now you can of course plot the, so this is the psi of x that I have plotted. So this is psi 3, this is psi 2, and this over here is psi 1x. Now what you have to remember is how the number of nodes are also going up. How many maximas do you get in the probability? All right. So these are the kind of questions that you can be asked. So I have put in some of those things in the assignment and I would like you to take a try at them. All right. Now let us look at the situation for the finitely deep well. All right. So let us look at the ground state solution once again. Okay. So let us say this is your x is equal to 0. This is your x is equal to L. All right. And let us say this is your E1, which is, this is your level. And if you had a finitely deep well, this is how your wave function would look, going exactly to 0, all right, at the edges. All right. What about if you compare it, if you said that I have exactly the same width for a finitely deep well, how would my wave function look? So what you have to remember is that the wave function will have a smaller height. It will look more or less the same, but then it will leak out of the well. Okay. So essentially now, please note your wave function. I should have drawn this a bit better or with a different color. iScribe actually allows it. Okay. This over here is for the finitely deep well. And what I want you to remember is that it is non-zero outside the boundaries. Okay. So that means there is a finite chance that the particle, okay, will not remain confined in the well, but it can actually leave the well. All right. So it is a small possibility. So it is non-zero here, unlike the case of the finitely deep well, where you can see here and here the wave function has gone exactly to 0. However, that is not the case with the finitely deep well. Okay. So in your mind, okay, so though we'll be doing almost all the problems with the infinitely deep well, the finitely deep well is a more complicated solution. Okay. You have to do a parametric solution. All right. So it is not so easy to remember that solution non-trivial. You have to derive it. But this is a way you can actually remember the comparison between the two, how it is for the finitely deep well and how it is for the infinitely deep well. And the key differences, as I told you, in the case of the infinitely deep well, you have an infinite number of bound states, not so in the case of the finitely deep well. And in the finitely deep well, the wave function leaks out of the well. Okay. So which means there is a non-zero probability of finding the particle outside the dimensions of the well. All right. So there is a finite probability of leakage, so to speak. All right. So what I'm going to do is I'm going to stop the share here. All right. And I'm going to share with you some of the problems that I have put up for. Okay. Let me see. There it is. I hope that's the correct one. Yeah. So I would like you to try doing problem 1. All right. So what is this? It just tells you plot En as a function of n. Okay. N is the number of the energy level for an infinitely deep well. This is just, to get some of the math out. And if you now define this delta En as equal to En minus 1 with this fictitious energy, okay, there is actually no E0. Okay, you just define this E0 as 0. Because sometime when you have to put E1, n is equal to 1, you're going to get E1 minus E0. Okay, so that's essentially the energy of the first level. You're putting in a fictitious E0. Fictitious means it doesn't really exist. All right. And what I'm asking you is to plot this delta En, all right, as a function of n. Then I've asked you the nature of the plot, and if it is linear, please give me the slope and what is the intercept. It is just to, kind of look at it in a slightly different way. There's nothing complicated about it. You'll be able to do it. Next thing what I've asked you is that you have a wave function of a particle trapped between x is equal to 0 and x is equal to L, and it's given like this, okay? So you can see it is given as a sine 2 pi x by L. Now, if you remember what was your solution, it was sin x is equal to a sine n pi x by L. So obviously you're clear now that this is essentially for n is equal to 2, right? So if it is for n is equal to 2, you know how to plot it. All right. So let me just get back to the ice cry. All right. I have to actually, sorry about that. I shouldn't have done that. I'll stop the share. All right. And then just get back to the ice cry. Yeah. So you know that essentially the solution looks something like this, right? If this is of course psi 2x, right? The wave function for n is equal to 2. Find out what is the probability when psi 2 for psi 2x. Okay, so you'll have to take mod psi 2x square. You will realize that you get 2 peaks. All right. So either from symmetry considerations, you can find out where those peaks are maximum. All right. So let me again get back to that question. Yeah. Oh, what did I do? I thought I had shared that. It's not my date today. Yeah. So what has been asked is that find the values of x where the probability of finding the particle is maximum. Okay. So once you have plotted mod psi x square, either you can look at the symmetries and get what is the maximum. I would like you to do it by both methods. The other method, of course, would be to differentiate mod psi x square. All right. Differentiate it with respect to x and find out where you are going to get that differential to be equal to 0. I assume that all of you know how to find maxima minima. Please try it in both methods. I would of course suggest that in a competitive exam you have to do it with symmetries because you need speed. All right. But just to do it by maxima, to assure yourself that you can do it like that, so that when you get a more complicated function, you can do it in that way as well. Okay, so it's just a practice. All right. What is the third problem over here? The third problem essentially is find the ratio of the energies of a particle in a one-dimensional box of length A when it is in the ground and the third excited state. So I think this is a really simple one. You need to find the energy in the ground state. You need to find it in the third excited state. So please remember E2 is the first excited state. So the only trick over here is that they have termed it a little cleverly. Okay. So E1 is ground state. E2 is the second energy level and it's the first excited state. E3 is the second excited state. E4 is the third, E4 is the third excited state. So what have you been asked? You've been asked the ratio when it is in the ground and the third excited state, not third state, third excited state. So remember that links to the number 4. All right. So get the ratio accordingly. So don't fall for such tricks. All right. So I'm just telling you where you can be tricked. You will know the answer, but it will just, because you have, yeah, you have just missed that excited state or something like that. So be a little careful. All right. Don't let such trivial things catch you off guard. Now, this is a problem which I think I will try and solve for you. All right. So the ones in blue, okay, are essentially what I will be solving in class. Okay. And depending on how, it comes out, the solution for this, you should be able to attack the other problems. Okay. And wherever necessary, I have given you hints. So let's go ahead and look at this fourth problem. All right. So I'm going to stop the share. All right. Sorry. We should have at least read it, no, first. Yeah. Suboptimal operation today. Yeah. So, okay. So here you are. What does it say? There is a particle in an infinite square well, and it has an initial wave function which looks like this. Please take a note of this wave function. It is psi x, and I have put the time over here. Okay. The time is at initial time, and that initial time we are taking to be 0. All right. And then you have the wave function equal to ax into a minus x. And what is this a? It is essentially that this function will have this form when x lies between 0 and a. So let us put 0 in this. The moment you put it to be 0, you will realize that you're getting the wave function equal to 0. Correct? Agree? Similarly, when you put x is equal to a, okay, you will realize again this factor goes to 0. So what are 0 and a? They are defining the dimensions of the infinitely deep well. Okay, the wave function is going to 0 at the edges. So it is an infinitely deep well. Anyway, you've been told that explicitly as well. All right. And the dimension is, it's a length of a, or a width of a, and it is going from x is equal to 0 to x is equal to a. And that is also kind of evident from here, that when the x is less than 0 or x is greater than a, your psi x0 becomes equal to 0. All right. Now what you've been asked to find is psi of xt. All right. So let's have a look at this problem. And for this, you are going to have to remember a few things. So has everybody understood the problem at least? I feel like I'm just talking to myself. Yes, Chetan.
Yes, ma'am.
Okay.
Understood.
Okay. So now the question is, if you think about it, the problem doesn't, it doesn't look like a infinitely deep square well solution at all, right? What did it look like? So let me just share the ice cry. It doesn't look like an infinitely deep solution at all. So we have been told that the eigenstates, okay, what are they? What do they look like? They essentially look like some root 2 by L. Here, of course, that L is equal to A. Okay, so we are going to change root 2 by A, and then we have sine of n pi x by A. Okay, so this is how we expect the solution to look like. But what have we been given? We have been told that this psi x of 0 is equal to ax into, I think, a minus x or x minus a. What was it? Can somebody tell me?
A minus x.
A minus x. Okay. So can somebody tell me what really is happening over here? Why is it looking so different?
That's the form at time t is equal to 0.
Yes, time t is equal to 0. But what do you think is happening over here? So the answer is basically, Chetan is absolutely right. This is how the form is at t is equal to 0. All right. And what you have to understand is that it is not in a pure state. It's not just that it is in level 1 or it's in level 2 or it's in level 3. It's not in one of the eigenstates of the system. All right. So this is the important thing to realize. So what is it? So you should remember from your formalism that you should be able to write any dynamical state of the system as a linear combination of the eigenstates of an observable. What is your observable over here? It is essentially a Hamiltonian, right? Yeah, your Hamiltonian. Your science, these guys are essentially energy eigenstates, right? Correct? These are energy eigenstates. These are essentially eigenstates of the Hamiltonian. And the Hamiltonian we know is an observable, right? Which means I should be able to write this state as a linear combination of the energy eigenstates. Why do I need to do that? Can anybody tell me? Why is it essentially for me to find out how it is written as a linear combination of these energy eigenstates? Why is it essential? Any suggestions? I'm going to stop the share here and just ask, because these are slightly important topics. So I'm going to take a little bit of time on the infinitely deep well. And when we go to the other 1D problems, okay, you can just use the same concepts there. Okay. We will not spend that much time doing those. All right. Because it will be essentially what we are doing here. We are going to apply there as well. All right. So I just am asking you, why is it essential for me to figure out how this wave function can be written as a linear combination of the energy eigenstates? What do I finally need to give you? What is the final solution? Yes? Any ideas? Throw it at me. It doesn't matter. Wrong, right? As we speak, we learn. Okay? So there is no wrong answers, no right answers. Okay? We do a discussion. So can you tell me why this is essential? It's, if you remember, I have always given you roadmaps, right? So why is the roadmap, it is important to find out the linear combination of the energy eigenstates? Any ideas whatsoever?
Ma'am, as we have by the method we have solved the Schrodinger wave equation.
Right.
We got various, for discrete states.
Correct.
So essentially, by the nature of the differential equation, the solution should be a linear combination of the states.
Correct.
So we write it that way.
You're absolutely right. But in this particular problem, why is it essential to figure out how that linear combination can be written is what I'm asking. So just ask yourself the question is that what is the final solution that I have to give? I have to give you psi of x t.
At any time t.
Correct. So how do I write the time dependencies? Anybody else? I think Chetan may have the answer already. So how do I write time dependencies? Any
Linear
answers?
combinations of some eigenstates, exponential term.
Yes, absolutely right. And what does that exponential term involve, Manikanta?
That involving time dependence.
Yes, but what does it have? It has a minus IH cross. What is
T by minus I h cross t.
No, there is an E also, right?
Oh, that's minus.
There is an energy, isn't it? Yeah.
Okay.
So let me just share the I scripts. I'm happy, you all of you. So this is how it should be. Okay, you should all contribute to the whole thing. Keep thinking along with me, and then we all learn. All right. So let us look at it. Okay, you have an energy eigenstate, correct? Yeah. What is its time dependence? So if its energy is En, you should remember the energy is given by it may not be I, is it? It's not minus IH cross, right? I think it's IH cross. En.
Minus I by H cross.
It's minus I, is it? Okay, fine. Right. So it's minus IH cross ENT, right? So this okay, guy is associated with this time dependence. Okay, so the En is a very important part of it. So now if you ask me what is the time dependence of this guy, I cannot tell you, because depending how it is, you know, written as a linear combination of these psi n's, okay, each of them will have a different time dependence, right? So all that is going to play a role, isn't it? So that is why it is extremely important for me, all right, to figure out how this is written as a linear combination of these psi n x's. Okay.
Can you repeat this one more time, ma'am?
Yeah, sure. I'll do that. Let me just go to a new page because I've scribbled all over this one. Yeah. 1 second. Surely I'll repeat it. Okay, so let us, we have an infinitely deep square well, right? Yeah. And we have energy eigenstates, which are, let me just put it in a slightly different form. Okay, and this is nothing but root 2 by a sine n pi x by a, correct? This is the thing, right? Now, if the system was in just one eigenstate, what would be the full form? So suppose now system is in pure ground state. Okay, and then I ask you, okay, tell me what is this psi 1 x of t? What is this? Then you will say, ma'am, this is psi 1 x e to the power of minus I by h cross e1 t. Okay, this is actually the full form, correct? Similarly, if it was in pure psi 2 state, okay, it would be essentially psi 2 x e to the power of minus I by h cross e2t. Now what have I given you? I have given you essentially a psi x0, which is equal to a x small a minus x. All right, we know this is again the wave function in on, it's an infinitely deep well potential, and the system is in this particular state. What do we know? We know that this must be equal to summation over n, okay, psi n, okay, x into Cn, some linear combination like this. All right, and your psi x of t must be equal to summation over n Cn sin x e to the power of minus I by h cross En t. Okay, so please note this time dependence is very strongly dependent upon the sign. So I have to find this. Okay, if I cannot, I will not know what ENs to write in the time dependence. Is this clear now? Have I kind of gotten
Yes,
across?
ma'am.
Yes? Sorry, I shouldn't have changed the page. So any doubts, please? I'm just going to stop the share and just talk. So we will take a little bit of time on these problems because, as I say, you know, it is important to understand these so that, you know, later on you will not have any issues. You just keep whizzing through. Okay. Has everybody understood this? What I'm trying to say over here? Yes?
Yes,
Yes,
ma'am.
ma'am.
Okay, good. At least
Since
one.
the time, the term involving time has to do with the eigenstates,
Exactly.
we are supposed to expand the given function as a linear combination of the eigenstates.
Absolutely.
So that is the issue.
Absolutely. Yeah. So we have to do it. If we want to, if we see finally what is our aim? Our aim is we have to give the, let me go back here. we finally have to find out what is this guy, right? Without knowing what linear combination of eigenstates it is made up by, we cannot do it. All right. So this is basically the idea. So now let me tell you what are the steps that you always should take. Okay. So let me just start off. Oh, I've almost spent 1 hour. My goodness, I'm going a little super slow, I think. Okay, fine. So the first step, okay, and this is a little important when you do numerical calculations. All right, what was your wave function? Correct? Yeah. What you don't know is this A. Yes, you don't know this A. So very important first step is that find A. The small a you know is the dimension of the well. All right. But the big A you don't know. What is it? Remember, it is a normalization constant. It's a normalization constant. So your first step would be to essentially normalize your psi x0. Okay, normalize your psi x0. How will you do it? You will essentially have to do it. What are the limits of your wave? It is 0 to a. All right. Why don't you bother for less than 0 and greater than a? You know that the wave function is anyway going to go to 0 over there. So even if you did it, you're not going to get any additional terms, any additional factor from there. All right. So it doesn't matter. So you have to essentially take your psi x of 0 mod square dx, and this should be equal to 1. All right. If you do this, you should be able to find your A. All right. So this is step number 1. What is step number 2? So let me just note down. This is your first step. What is your second step? Your second step will be that you will now write your psi x of t, okay, as equal to summation over n, sum n equal to 1, it can go till infinity, okay, you need not stop. And then you will have your cn psi n x e to the power of minus I by h cross e n t. Okay. Now, what is this? You need to know about psi n x is that this is going to be root 2 by a. I have written this several times. I'm already boring you guys, but doesn't matter. N pi x by a. Another thing that you also know is that these form an orthonormal set. They form an orthonormal set. What does that mean? It means that each psi n x is normalized, right? It means that. And it also means another thing. And what is that? It means that when you do an integration from 0 to a of psi n x, psi m x dx, you will get a 0 when n is not equal to m. So essentially, if you remember, what I have written for you over here is the inner product or the scalar product. Okay, I've written the scalar product between two energy eigenstates of the Hamiltonian. And the inner product of those will be 0 because these states are orthogonal to each other. So now using this and using this, we should be able to find out the CNs. Okay. How do we do this? So let me go further. So essentially, what are you going to do? Suppose I want to find out what is Cn. Then I should do this. I should do an integration from, okay, I made a mistake over there. Please, let's get back to the earlier page. Can anybody tell me what mistake I made? Inner product, I should write this as star, okay? Psi n star x, okay? It didn't come out too well. But here it doesn't matter because these wave functions are real, okay? But still, I shouldn't have made that mistake, all right? So here, what should I do, okay? I can do now psi n star x, okay? Psi x0 dx, all right? If I do this, oops, I forgot to change page. Very, very sorry. Okay. So let me just write it again. Cn is equal to 0 to a okay. How do we know this is actually true? Because please note, if you did a 0 to a integration of sin x, okay, and then what will you have over here? You'll have a summation over n Cn, okay. So I will write these as m, okay, dx. What will this give me? It will give me an integration. Okay, I will write it differently. I'm going to pull out the summation over m Cm. I can always change the integration and the summation. I can swap them, you know it, all right? And Cm is of course a constant, okay? So I can pull it out and then I'll have an integration over here of psi n star x, I m x dx. This of course going from 0 to a, right? And this we know is nothing but delta nm, where your delta nm is of course your Kronecker delta function. It is equal to 0 when n is not equal to m, and it is equal to 1 when n is equal to m. Correct? So what will we get now? We will get over here summation over m Cm delta nm, which means that we will get Cn. Cn. All right. So essentially, you have to work out this formula in order to be able to get your Cn's. So how do we do it? We will write down your Cn is equal to summation 0 to a. Now remember, this complex conjugate we need not worry about over here, but the only reason we need not worry about it is our eigenstates are purely real, okay? Otherwise, that has to be taken into consideration, which is why I wrote it merrily as Cnx over there, sin x over there. I shouldn't have, okay? I should have written the complex conjugate. So what do we get now over here? We will essentially get your root 2 by a, okay? And then you have your sine of n pi x by a. And then of course, you have your a, which you will have found out from your first step. And then you have x, you have a minus x. This is the form of, what is this? This is nothing but your psi x0, right? Dx. So figure out what is this integration. All right, this will give you all the Cn's, and then you will be able to write your psi x0 as equal to summation over n. You will have your Cn, you will know that, and you will also have your psi x. What is the next step? The next step then is to just write down. So this is, you can say, is your third step, and your last step then will be to just write this is equal to n Cn psi nx e to the power of minus I by h cross E. Is this clear? Has everybody understood the roadmap?
Yes, ma'am.
Has everybody understood the roadmap? So I don't think there is any time to really do this. Yeah, I've already overshot your limit. All right. So I will not do it over here. So what I will request is that I'm going to send that part of the assignment where there are these simple problems on infinitely deep well, and I will also send my notes, and I will send you this problem which we were supposed to solve totally in class. Okay. And we will discuss this problem. Okay. This one which we were supposed to solve totally in class in the next class. But since I have given you the steps, I think you should be able to also do it on your own. Okay, so we will discuss it in class. All right, so I don't want you to send it to me as an assignment, but if you look through how to solve it, okay, and understand the steps, I think you will find it very easy to do it next time. All right, we will not really work out each and every step. We will just do it rapidly. Is that clear? Yes. Okay,
Yes.
so what am I
Yes,
expecting by
ma'am.
next class? Yes, Nitin, you had a question.
No, ma'am, I was responding.
Okay. What did? Okay. Huh. So the thing is that for the, I'm sorry, I'm just not getting the words correctly today. What did I want to say? Yeah. So the free particle problems, I think there's essentially one problem that I would really like you to do, the last one. That and the infinitely deep problems, the simple ones. Okay. I would request you to try and solve them and send it to me by the next class. All right. So that will be good. So those we will not really discuss in class. I will discuss in class once I have looked through your assignments. Is that okay? Is that all right?
Yes, ma'am.
Yeah, good. I would like people to contribute to the class as we go along, okay? Because that's when I know that if there are any doubts, please ask me, okay? Don't sit quietly, because yeah, it is not good for you. It is certainly not good for me, okay? Yeah, because I just assume that you have understood, which is not good. All right. So fine, then we will stop the class, and thank you once again for allowing me to take this class at this particular point of time. And I'm really very sorry for having missed it earlier. Okay. I will try and not let this happen again. All right. So take care.